Physics reaction video number 73. Had to take a little bit of time off to do some other work, but now I'm finally back to it, and I really enjoy doing these, so I'm happy I'm able to. Today I did a search for hydrogen atom homework. Let's see what we can get.
All right, sorry for the delay there. We sort of got some practice with solving three-dimensional problems looking at the infinite spherical well, which is already complicated, at least in the L not equal to 0 case. But we've seen, a lot of the work has been done, and we really just need to solve that radial equation in which the potential.
So I think what's happening here is this is a hybrid class, because this camera is clearly set up to see the chalkboard, and he's looking at somebody else. So I think that's what's happening. And we can sort of tell where they're at. This is, my guess is like a modern physics course, because what he just said they did was the spherical potential well. So basically no potential energy in the middle, and then infinite potential energy once you get outside of a sphere. And people do that because it's got the spherical symmetry that the hydrogen atom has, and but slightly easier sort of boundary conditions to deal with. Whereas when we get to this potential energy, it gets a little nastier. So it's really tough, lots of mathematics often. And I'm always curious to learn better ways to teach this material.
Still appears, right? We've already got the theta and phi dependence from the spherical harmonics. As long as your potential is only a function of r, that work is done. And now the only remaining work is to put in your potential into the radial equation. So here we're talking about the potential energy between an electron and a proton. That's a hydrogen atom, right? And we're going to pretend, this isn't exactly true, that the proton is, like 2,000 times as massive as an electron. So when the electron's orbiting the proton doesn't move much classically. So we're going to pretend it's fixed at the origin, and the potential energy represents the potential energy of the electron-proton system as a function of the electron position.
So what's interesting about what he was just talking about is often in, at my school, the curriculum, I guess it would probably be the next year, they take a theoretical mechanics class that talks about how, if you have a central force, you really can do this center of mass frame, and you really can reduce it to what feels like a one-particle system. What's interesting about quantum mechanics is you sort of second-guess every potential assumption. So here he's saying, let's just say that it's so heavy it doesn't move. So that's why we'll call it a one-dimensional problem. But I think that students might wonder, and I think you basically can do this, could you just do the reduced mass approach that they, at my school, they wouldn't be learning about it in this semester. They'd be learning about it in the next semester. But this reduced mass approach can make you feel better about this, what's going on here, because it's not an approximation, actually. It's just a different frame of reference to look at this very same problem, which reduces to a one-dimensional problem.
And from physics 230, that's, that electromagnetic K, which is 1 over 4 pi epsilon 0, times Q1, Q2 over R, and in this case, the charge on the proton is little e, charge on the electron is minus little e, so we get a minus little e squared, and we plug that into our radial equation, which you may remember has this sort of kinetic-looking term, and then there's the effective potential, and I guess I should mention a little bit. Do you guys talk about effective potential for those of you who took advanced mechanics? I'm assuming you talk about it in there.
Wow, that's super interesting, right? So he has an audience that has taken that mechanics class that I talked about. So what's interesting in that mechanics class is this term, it never looks like this in a mechanics class, but this sort of effective, centrifugal barrier comes about because there's basically no theta term in the Lagrangian. So those of you who don't know what I'm talking about, you can just ignore me. But what happens is you get, oh my gosh, you look at this and you do the Euler-Lagrange equation, you're like, wait a minute, there's no theta in here, so there's a constant, let's call it angular momentum. I guess that's not when it gets called angular momentum. But what happens then is, ooh, wow, we could actually approach this from a different perspective. And when we're thinking about forces, we can basically pretend there's this outpushing force, because that's one of the consequences of reducing a three-dimensional, or really a six-dimensional problem, because there's two particles. You have two particles in three dimensions, that's six. You do the reduced mass, that gets it to just one particle, mythical particle, which is three, but it turns out it has to stay in a plane, so that gets rid of one. And as you're doing all of that work, this is the last piece where you do the angular momentum piece. You just have to say, okay, in this mythical one-dimensional problem, we have this extra outpushing force. Now, in quantum mechanics, this comes about from a completely different perspective. You do this, you have this differential equation, and you separate your variables, because there's these R derivatives, and you have the thetas and the phi variables, and it turns out everything's separable. So you get all these constants lying around. One of them we decide, trust us, wink, wink. Let's call it L times L plus 1. You'll trust me later. Of course, the students are just thinking, it's just a constant. Why are we calling it L times L plus 1? But of course, it works out. So I love the fact that he stopped and asked the question whether they had seen it before. But yeah, this is just representing, hey, I'm attracted to you. Oh, wait, for some weird reason, I'm repelled from you. Oh, it's because we're doing this in one dimension. But we're not writing a Lagrangian anymore. We're writing a Hamiltonian. So that's why there's a plus here instead of a minus. And also why there's this extra constant, because we had this separation of variables thing.
The idea is, if you think of something orbiting another object, Earth orbiting the sun, or you going on a merry-go-round spinning in a circle, right? If you're not spinning at all, that's the case L equals 0. This L we're going to see corresponds to orbital angular momentum. So L equals 0 means 0 orbital angular momentum. The effective potential is just the regular old potential. And in that case, you would say, okay, that's like being on a merry-go-round, and there's no problem walking towards the center. Or if Earth is orbiting sun, but here we're imagining it's not orbiting at all, it's going with 0 velocity, so it's just sitting there, right? The only potential energy that you effectively feel if you're riding along with Earth is the potential energy, gravitational potential energy, the usual V of R. So that would be something like this, but the gravitational analogy to that. Whereas if you're spinning around on a merry-go-round, right, in addition to the potential energy, just to stay at a certain radius of orbit, you have to have a force towards the center. Like I might have to be holding onto a rope as I'm going around on the merry-go-round. And I think of that force as being associated with the potential energy, right? I think, oh, okay, I've got to pull in this direction, or something is pulling on me, and there's a potential energy associated with that. Now, there's not actually any potential energy associated with it. It's because you're viewing things from a non-inertial reference frame. But you can think of this term as characterizing the faster you are rotating around. In other words, little l, the bigger little l is, the more angular momentum you have, the harder it is to get towards the center. It's like there's some additional potential energy repelling you from the center. Repelling because it comes in with a plus sign here rather than the minus sign. This is an attractive potential energy. This is repulsive, really, and it means it's when you're spinning in a circle around something, it's really hard to move towards the center. As you get closer and closer in, you're spinning faster and faster, and it's really hard for you to get close to the center of rotation. Several of you in reading responses asked about the effective potential, and that's the idea. It's when you're moving with the thing that's going around in a circle, this feels like it's your potential energy. Now, we know from Newton's point of view, that's a non-inertial reference frame. You're sort of accelerating as you go around. And so we wouldn't say this is really part of the potential.
That's so interesting. In a mechanics class, it is sort of always put, scare quotes around it, like, oh, it's not really a potential energy. It's just how you feel. And we talk about, oh, you're in a non-inertial frame. We're not actually saying that the electron is in a non-inertial frame. This actually came about from separation of variables. It was just straight up differential equations, right? I mean, hey, we have this crazy differential equation. We've got r's and thetas and phis. And, oh, let's see if we can gather all the r terms in one place and the thetas and phis on the other side. Oh, my God, we did it. We get this L times L plus 1. And at the cost of some weirdo constants starting to float around, specifically this one here. Well, we got two constants, this one and this one. And I think that I don't think we would say that well, therefore we're treating the electron as though it's in an non-inertial frame. So it's fascinating that these two things really are doing the same thing, and yet we represent them in such different fashions in a mechanics class versus a quantum mechanics class.
Potential energy. The potential energy is just the forces we normally see, and this is the only part that's a real force. But in order to stay on a circular orbit, you have to apply an additional force towards the center, or you feel like you're being thrown outward due to that fictitious centrifugal term, or centrifugal force, which corresponds to this centrifugal term. In any case, this is our radial equation. We're just going to think it's a differential equation, kind of a monstrous differential equation, and we got to solve it now. And we're going to do that in steps to try to simplify it as much as possible before we get a series solution. Okay, you might just say, well, let's try to get a series solution. And you can always do that. If
Sorry, I just wanted to correct myself. This one came about because there was also a time derivative in there somewhere. This one came about from the time derivative. Sorry. Just going to go back. I do really, really like how this looks, right? If you're used to one-dimensional Schrodinger equations, you got two space derivatives, something times the wave function equals energy times the wave function. So the something is really supposed to be the potential, right? So I just love the way he represented it. From now on, we're solving a one-dimensional problem with a really, really interesting potential energy. And of course, the most interesting part of it's a potential energy that very smoothly goes to zero as r goes to infinity, as opposed to like a square well that just abruptly changes in certain places. And so only at r equals infinity do we have some interesting boundary conditions to match, which sucks, right? I'd rather have that happen at a non-infinite value, like an infinite square well or something. But yeah, now it's just math. Let's go and let's learn what we can about this function u as a function of r, and then depending on what l's are allowed and all of that stuff. Yeah, super interesting.
We try to get a series solution, you're going to get some very unfamiliar kind of recursion relation for the coefficients in your series solution, and you'll end up with a function that you've never heard of before. You can give it a name. You can always name a series that doesn't match with any other series that you've gotten before.
That's awesome.
But you'll have very little insight into it. So by doing this pre-preparation, we're going to turn the solution into something that formed out of pieces that we actually understand. Now, let's look for the bound states. For the bound states, we're talking about, why are the bound states less than zero? Well, if we look at the real potential energy, not the effective potential.
Ooh, cool.
Uh-oh. Let's refocus the camera here.
This is cool.
Our potential energy, which is K, Q1, Q2 over R, V as a function of R, the real potential energy, not the effective potential, is negatively proportional to 1 over R, right? It's minus K E squared over R, right? If I put in the two charges, E and minus E, and K is 1 over 4 pi epsilon 0. So that means...
So he's got autofocus on the camera, which really sucks, but usually when he's really making a point, he's standing over there, so it's going to keep the chalkboard in focus when he's standing over there. But it would be nice if it could just stay focused on the chalkboard the whole time.
Means energies down here are going to correspond to bound states. And if the electron has an energy up here, that's going to correspond to a scattering state. So we're going to start out looking for the bound states, which are the ones you concentrate on, and mostly the ones we're concerned with, because when we talk about an atom.
It's really interesting when he's talking about these scattering states and these bound states. I'm trying to decide if you really need to draw the effective potential instead of the actual potential. I think you want to do the effective potential because you have this. What's going to happen, of course, is it's going to go like that, and so there's going to be this little pocket where things can be bound. And if we're just talking about lowercase r, I do think you need to do this from the full, I guess, what do we call it, effective potential. Because to think that there's a particle that sort of lives here would be like, why would it ever live here? It just should dive down to r equals 0. And by the way, of course, because we're using r less than 0 has no physical meaning. So really only r greater than 0 is real. These scattering states, they have an L, right? You shoot an electron at an atom, it's going to have an L, an angular momentum. Yeah, I think you need to put the effective potential here, but so far everything he said has been right. I'm just going to keep an eye on when you really need to be talking about the effective potential versus the so-called actual potential.
We're not talking about a proton and an electron that's zipping by under the influence of its force. Usually we mean it's bound in some state. So we're still out of focus a little bit. That's better. Okay.
It's a cool fix for his focus.
Okay, so bound states correspond to energies less than 0 in this case.
I like this multiple.
Now, if the energy
stuff
is less than 0, usually the way we proceed is to multiply, or divide by this constant on both sides to get the second derivative by itself. And when we divide by this, in other words, multiply by minus 2m over h bar squared, we get a minus 2me over h bar squared. But E itself is negative if we're looking for bound states. So minus E is positive, right? And so we make that usual definition. Let's define kappa to be the square root of minus 2me over h bar. In other words, the square root of the thing that appears on that side after we divide by those constants in front of the second derivative. And for us, that's just a simplifying thing, right? We're going to go back. We'll be interested later in the energies, so we have to remember things will be written in terms of kappas. And in fact, we'll make several other variable transformations to make our life easier. But ultimately, we're going to be interested in the energies.
Students might disagree.
So we're trading those out for kappas now. Here's our first other of the other transformations. We're now going to change the independent variable here. So, right, you have u is the dependent variable of the solution, and u is a function of r. That's the independent variable. And to simplify things, we're going to change it to be a function of rho, which is kappa r, defined as kappa r. And worksheet 1 is, Griffiths doesn't really say anything. He just tells you what the solution is. So let's try to do this. And I want you to think about it for a couple of minutes and see if you can start doing that. I want to write this.
So I think I want to pause here, possibly even stop here. I'm just so fascinated by how to set this up. Honestly, the way I've approached it, I'll maybe put a link down below, is once you have this, if students are used to seeing some numerical solutions, dump this into a computer, start looking at some numerical solutions. What you'll find is there's only certain energies that have this function not run away to infinity. Right? We can't let the probability run away to infinity, so we need to sort of futz with this value here until this function u looks sort of normalizable, right? And when you do that, you stare at the energies you get, and lo and behold, it's negative 13.6. It just comes, negative 13.6 electron volts is when this thing is nice and calm, and you say, boy, can I find other solutions? And oh my gosh, every time I do, it's negative 13.6 divided by some integer squared. What the heck? I don't understand. Why is this happening? Right? So from the perspective of what this thing looks like, you're done. Slap this into a computer. Let's really go investigate which energies are allowed. But what he's setting up is an awful lot of sort of, as he said, variable substitutions and some really smart math. One of the things that can be done is let's look at really big R's to make all of this stuff go away. Well, if you make really big R's, you have a pretty easy differential equation, right? Or you can do itsy bitsy little R's, and then things get weird. You can see that, I'm sick and tired of writing all of these constants, so let's see what happens if I just sort of renormalize everything. It's still going to have roughly the same look to it. Everywhere there's an R, there's going to be a rho, but there's going to be extra kappas floating around. There's just so many ways to do this problem. And I'm just struck by this analogy to when they see it in a mechanics class, because we're doing it in such a different way. Man, this was cool. First of all, I love the setup. I love the talking and the camera and the screen. That was super cool. I really liked how much time he spent on this. This was really, really cool. And I think that you can tell that he's really trying to connect. He even asked, like, hey, have you seen this before? So very cool stuff. Man, I'd love to keep going, but this video has gone on for a while, so I think I'll stop here. I'd love to hear how you guys approach this problem. All right, everybody. Hope you have a great day, and remember, physics teachers are awesome.